Welcome to the Rockwell Collins MultiScan Radar computer-based training program. Let's get started by looking at MultiScan controls and displays. The Airbus Radar Control Panel System Switch is a three-position switch. The center position turns the system off. The number 1 position selects the left receiver transmitter, or RT, and the right position selects the right RT. The predictive wind shear switch disables the automatic wind shear features. Today's digital low-power radars are not a significant radiation hazard. It is recommended that this switch be left in the auto position. However, since the radar weather scan is reduced to 120 degrees when wind shear is activated, pilots can temporarily select PWS off in order to get the full 180-degree weather scan. Once the weather is examined, the switch should be returned to the auto position. The MultiScan switch toggles between the radar's auto and manual modes. During manual operation, the ND displays MAN in front of the tilt code. In manual, the radar works exactly like a traditional radar. During auto operation, only the tilt code is displayed. When the radar is in auto, the radar's automatic threat and weather detection features are activated. Weather radar is, of course, all about showing weather. When the radar is in auto and weather mode is selected, the radar's essential automatic features are activated. MultiScan uses multiple sweeps to collect weather and terrain information, stores the information in a temporary memory buffer, eliminates the ground clutter, and displays the weather. In these pictures, note the absence of ground clutter and the thunderstorm cells at 60, 130, and 180 nautical miles. In addition, the radar displays a fourth cell that is over the horizon. The yellow arc is a pack alert function and warns crews that the cell at 60 nautical miles is attenuating the radar beam, and the area behind the cell is not visible to the radar. Pack alert is only active during auto operation when cal gain is selected. One significant difference between MultiScan in auto and a traditional radar is that weather below the aircraft flight path, or non-threat weather, is not displayed. MultiScan uses the quiet dark cockpit philosophy. In other words, if it is not a threat, it is not displayed. Note the flight path vector on the HUD display, and also note that it is intersecting the 0-degree pitch line, indicating that the aircraft flight path is above these cells. Also note that the display shows a clean screen since the non-threat weather is not displayed. Non-threat weather is often visible from the cockpit, and there are occasions where it may appear that cells should be displayed, but are not. For instance, this cell is not displayed, but is it at the aircraft altitude? How about now? The fact is that this is a post-convective cell. On close approach, it can be seen that there is no substance to the cell. In fact, you can see right through it. In addition, the cell is 1 to 2,000 feet below the aircraft, and thus not a threat. Again, applying the quiet, dark cockpit philosophy, this non-threat cell is not displayed. A quick note on radar beam width. Although a 3-degree radar beam is pretty narrow, the fact is that at 80 nautical miles, it is already 25,000 feet in diameter. What this means is that even when the radar uses multiple scans, the height estimation of the cell becomes more and more coarse the further the cell is from the aircraft. So on occasion, weather that is initially visible at longer ranges may fall off the display as it approaches the aircraft, and the radar can better determine the cell heights. Remember that when the radar is in auto and the weather mode is selected, the essential MultiScan automatic features are activated. In weather mode, the radar paints the standard red, yellow, green, and black radar colors. Remember that black is a radar color. Black does not mean that weather is not present, but only that the weather is not reflective enough to meet the green threshold display criteria. WX plus T enables the essential MultiScan automatic features and Doppler turbulence detection out to 40 nautical miles on all range scales. Turb mode presents just the magenta turbulence indication without the green, yellow, and red weather depictions. Turb mode should be used on a momentary basis only to identify areas of turbulence. Pilots should then return to the weather or weather plus turb mode so that the full extent of the weather system is visible. Map mode displays all the information that the radar sees, both ground and weather returns. The ground clutter suppression switch is similar to map mode, except it is a spring-loaded momentary function. The tilt control is inactive during auto operation. Full above and below calibrated gain is available during both manual and auto operation. When the radar is operated in manual and calibrated gain is selected, standard radar reflectivity rain rates are displayed. An increase or decrease of 10 dB of sensitivity represents a change of one color level. Increasing the gain to max increases the sensitivity by 16 dB, or an increase of 1.5 color levels. Yellow will display as red, and green will display as yellow or red. In addition, areas of black may display as green or yellow. Conversely, selecting minimum gain decreases the sensitivity by 14 dB and reduces the color levels approximately 1.5 times. Thus, green returns and a significant portion of the yellow returns will disappear, and red will turn to yellow or green. Essentially, in min-gain only thunderstorm cores are displayed, and they will be represented as green or yellow. Min-gain should be used for momentary weather evaluation only, and then the gain should be returned to the cal gain position in order to avoid underrepresenting the thunderstorm threat. Man gain is displayed above the tilt code when the radar is in any position other than cal. Now let's explore gain in auto mode. A typical thunderstorm is very reflective below the freezing level. However, the top third of the storm tends to be glaciated and non-reflective. As an aircraft climbs, the radar beam moves higher in the cell and, at cruise altitudes, can overscan the reflective portion of the cell, resulting in inadvertent thunderstorm top penetration. In auto mode, MultiScan uses an automatic temperature-based gain to reduce this threat. As the aircraft climbs and the outside air temperature decreases, the radar automatically increases gain to compensate for the lower reflectivity of upper-level thunderstorms. So let's see how this works in actual operating conditions. This example shows a typical low reflectivity oceanic cell. With manual cal gain selected, only the core of the thunderstorm is visible. In manual max gain, the greater extent of the thunderstorm is visible, and the cores are now red. In auto cal gain, the radar has automatically increased the gain as the outside air temperature decreased, providing a picture that is very similar to manual max gain, reducing the threat of inadvertent thunderstorm top penetration. Note that at cruise altitudes, manual max gain and auto cal gain are essentially equivalent. In auto, further increasing the gain above the cal position may result in overwarning and unnecessary deviations. Rockwell Collins recommends that the radar be operated in auto, cal gain, and WX plus T in all phases of flight. The one exception is that at top of descent, it is recommended that manual momentarily be selected to examine weather along the descent flight path. In summary, remember that full above and below gain is available during both manual and auto operation. Also, there are three major differences between operating the radar in manual mode and in auto mode. First, when operating in auto mode, the tilt control is inactive. Second, in auto mode, MultiScan utilizes the quiet, dark cockpit philosophy, and weather that is below the aircraft flight path is not displayed. Third, Automatic temperature-based gain increases the gain as the aircraft climbs into colder regions, resulting in a picture that is very similar to manual max gain at cruise altitude. Operation in cal gain while in auto is recommended. It's been said that beauty is in the eye of the beholder. We could say the same thing about the color green and its meaning on the radar display. The fact is, depending on your manual operating techniques, green may mean very different things to different pilots. For instance, in low reflectivity environments, some flight crews use a low tilt setting and max gain, and then avoid all weather that paints yellow or red, under the assumption that the threat reaches to their altitude. In these instances, when auto paints the cell green, the crews consider that the radar is under warning. However, other crews in similar environments use a higher tilt setting and calibrated gain. In these cases, most thunderstorm cores paint green on the display, and these green cores are considered a substantial threat. When MultiScan paints the core red, as in this picture, and the edges of the cell are displayed as yellow and green, these crews consider the radar to be overwarning. As we learned in Module 1, MultiScan uses variable temperature-based gain to better detect low reflectivity thunderstorm tops. The end result is that most flight crews will see more than they are used to seeing when using the radar in auto. This series of pictures is taken over the Gulf of Thailand. Note that in manual mode, in calibrated gain with a -2 down tilt, only thunderstorm cores are shown. When manual max gain is selected, a weather ridge line is visible to the flight crew. Because the Gulf of Thailand is a low reflectivity environment and cells are difficult to detect, auto cal gain is actually more sensitive than manual max gain and displays more of the cell system for the crew. So, here are some guidelines for interpreting the radar display, and especially the color green, during automatic operation. First, let's consider low-altitude operations. There are many times where the color green is not a threat and indicates at most light to moderate chop. For instance, consider this picture where the entire display is green. At lower altitudes, this occurs during stratiform rain conditions, and little to no turbulence is present. At lower altitudes, there are occasions during certain unique meteorological conditions where the display may turn completely yellow or even red, which is sometimes called redout. In this instance, the aircraft is right at the freezing level, and melting snow has formed an area of strong reflectivity, turning the display yellow, even though there is very little turbulence. A similar situation sometimes occurs during monsoon rains, where heavy rainfall rates produce very strong reflectivity. Remember from Module 1 that every 10 dB of gain represents one color level. Therefore, should flight crews encounter a situation such as this, gain can be temporarily reduced to -9 or about one color level to better determine if embedded cells are hidden by the heavy stratiform rain. During high-altitude operations, interpretation of this picture changes. In this case, a broad area of green may indicate high-altitude ice crystal conditions. As this satellite picture shows, ice crystals can be present over a broad geographic area. These ice crystal clouds have resulted in TAT anomalies and engine power loss. The new high bypass engines appear to be especially susceptible. In this case, the aircraft transiting the area experienced TAT anomalies about halfway through the ice crystal region, and the anomalies stopped shortly after exiting. Initial flight tests and incidence reports have shown that when in auto, the radar's variable temperature-based gain function often displays these ice crystal clouds. If a broad area of uniform weather such as this is displayed at higher altitudes when using the radar in auto cal gain, crews should consider this a potential area of high-altitude icing. Exit the region as soon as practical. As can be seen by this view out the captain's window, the radar is displaying weather at 25 nautical miles. In this case, green represents a pressure ridge, and the flight crew can anticipate light to moderate chop when the aircraft transits the region. However, the two fingers that extend to the right of this storm core indicate an internal shear force. Even though these returns are green, they still represent a threat to the aircraft. In fact, this dark area between the two fingers is an indication of a hail shaft and should not be transited. This 787 display shows normal thunderstorm activity. The circular shape of the cells and the normal gradient between colors indicates convective activity but no unusual threats. In this case, green represents the outer boundaries of the cells, and the pilot navigated between the two cells containing yellow cores. By way of contrast, the irregularity of these cells indicates significant shear activity, and the very steep gradient between the colors is typical of very strong convective lift. Once again, these U-shaped areas represent possible hail shafts. With regard to these cells, green is a good color to avoid by a wide margin. Increase in green returns will also occur as weather nears the aircraft. By way of explanation, let's examine radar beam attenuation. When a radar pulse leaves the aircraft, some of it is scattered and absorbed into the atmosphere. This attenuation of the pulse grows in magnitude as the distance of the pulse from the aircraft increases. In addition, beyond 80 nautical miles, thunderstorms no longer fill the beam, and further attenuation occurs because there is less power on target. This means that at long range, the radar will only be able to see very strong weather, such as thunderstorm cores. As these storms approach the aircraft, more of the cell becomes visible. In these pictures, note how the radar sees the line of cells at 300 nautical miles. As the cells approach the aircraft, attenuation is lessened, and more of the full extent of the storm becomes visible to the radar. What this means is that it is not unusual for storm cells to fill in as they approach the aircraft. In fact, due to features such as geographic weather correlation and automatic temperature-based gain, the radar now sees more of the actual extent of the storm than could be seen with older radars. Note in this picture that at 50 nautical miles there is a gap between the cells. However, when the cells are at 40 nautical miles, the radar attenuation has lessened, and it can now see the green haze between the cells. There will be occasions, such as this, where a transit corridor between two cells fills with green as the aircraft approaches. Again, remember that in these situations, green normally indicates light to moderate chop and can be transited. In summary, when interpreting the color green on the radar display, perception as to whether the radar is under warning, overwarning, or just about right will depend largely on your previous manual operating techniques. However, in most cases, due to the radar's use of variable temperature-based gain and geographic weather thresholds, most pilots will see more information than was previously available. Remember that in many cases, green represents at most light to moderate chop and can be transited. However, pilot interpretation of the radar display is still critical for avoiding significant convective activity. In this case, shear forces associated with an adjacent thunderstorm represent severe weather and a possible hail shaft. Also, normal cells are circular or oval in shape and have normal gradients, while irregular cells with steep gradients represent a severe threat. If a red-out condition is encountered that saturates the display, turn the gain down to -9, or about one color level, to check for embedded cells. After momentarily analyzing the weather, return to the cal gain position. At cruise altitudes, a region of green on the display may represent high-altitude ice crystals. Exit the region as soon as practicable. Finally, remember that as the aircraft nears weather, there will be less attenuation, and that more green returns will become visible. Rockwell Collins' new ThreatTrack software enables 6 new weather analysis tools that assist flight crews in assessing actual thunderstorm threats. Note that on the MultiScan ThreatTrack control panel, the TURB function has been removed and replaced with a Weather plus Turbulence plus Hazard selection. When Weather plus Turbulence plus Hazard is selected, MultiScan's ThreatTrack features are added to the essential automatic MultiScan capabilities previously described in Modules 1 and 2. ThreatTrack is based on Rockwell Collins' Track While Scan technology, which is described in detail in Module 4. Track While Scan enables the following new features: Core Threat Analysis, Predictive Overflight, 2-Level Enhanced Turbulence, Mid-Altitude Associated Threat, Mature Cell Associated Threat, and Anvil Top Associated Threat. A key design goal for ThreatTrack is to make the colors displayed on the ND more representative of the actual thunderstorm threat. When the Track While Scan technology determines that the convective activity is more intense than the precipitation level would normally indicate, Core Threat Analysis increases the color level to more accurately represent the actual threat. When compared with this ground-based radar threat image, it can be seen that Core Threat Analysis enables a better representation of the actual cell threat. In cases where the convective activity is already properly displayed, colors are left unchanged. Thunderstorms can grow as rapidly as 6,000 feet per minute. These rapidly growing cells push a turbulence bubble above them as they grow that can produce severe turbulence even though the aircraft is several thousand feet above the visible top. Predictive Overflight uses ThreatTrack's Track While Scan technology to detect and measure cell growth rate and then predicts the resulting bow wave turbulence created by the storm. The cell may eventually appear on the display as it continues to grow toward the aircraft altitude. The Predictive Overflight icon is used to warn flight crews of the potential turbulence threat from a cell that is growing towards the aircraft's flight level. Note that this Predictive Overflight icon appears in the black, indicating a cell that is growing towards the aircraft's altitude. 2-Level Enhanced Turbulence measures severe and ride quality turbulence out to 40 nautical miles. When the new FAA standards for severe turbulence are met, solid magenta is displayed. When the radar detects less severe ride quality turbulence, consisting of light to moderate chop, then speckled magenta is displayed. MultiScan ThreatTrack's Associated Threat feature analyzes individual thunderstorms and infers the additional threat associated with the cell based on its intensity and life cycle development stage. During the early developing cumulus stage and late dissipating stages of the cell, threats are relatively minor. However, during the later stages of cumulus development, cells do become electrified around the freezing level due to the collisions between positively and negatively charged ice particles. The resulting electrical potential forms the basis for possible lightning discharges. During the mature stage of a thunderstorm, hail and turbulence may extend outside the cell boundaries, and severe cloud-to-cloud and cloud-to-ground lightning is possible. In addition, at cruise levels, hail may be thrown out of the top or sides of the cell and in the downwind direction. ThreatTrack's Associated Threat feature provides flight crews with a mid-altitude associated threat, a mature cell associated threat, and an anvil top associated threat that correspond to each of these 3 scenarios. The following is an overview of the 3 associated threat warnings. First, let's look at the mid-altitude associated threat warning. Toward the end of the cumulus stage of thunderstorm development, cells become electrified but do not yet have extensive high-altitude convective activity. Nevertheless, these mid-altitude cells do contain lightning potential. MultiScan ThreatTrack radar denotes this mid-altitude lightning threat by placing red speckles within the cell boundaries. This mid-altitude associated threat warning is displayed until the aircraft climbs higher than 10,000 feet above the freezing level. Second, during the mature stage of thunderstorm development, strong updrafts carry moisture aloft, with the result that there is high reflectivity at cold temperatures. These mature cells create lightning and hail potential and produce very strong turbulence. What's more, because the strong updrafts associated with these thunderstorms can exit the top or sides of the cell, the potential danger area for hail and turbulence can extend well outside the cell boundaries. In the case of a mature cell associated threat warning, MultiScan ThreatTrack extends the warning area outside the cell boundary to denote the increased threat from the mature cell. The associated threat icon for mature cells is displayed at all altitudes. Finally, above 25,000 feet, MultiScan ThreatTrack displays an anvil-top associated threat. The radar uses cruise-level winds to extend the threat region downwind of the cell. An example of this will be shown shortly. Note the more benign non-electrified cell directly in front of the aircraft. In this case, no associated threat icon is displayed. As explained earlier, mid-altitude associated threat consists of red speckles contained within the cell boundaries. These cells are potential lightning sources. Approximately 80% of lightning strikes occur within 3,500 feet of the freezing level. When electrified cells are present, and when it is practical, transit through the area near the freezing level as quickly as possible. Also, maintain an appropriate distance from electrified cells in accordance with company guidelines. Remember that the mid-altitude associated threat icon will no longer be displayed once the aircraft climbs more than 10,000 feet above the freezing level. In this example, the aircraft is descending from cruise altitude and is more than 10,000 feet above the freezing level. Thus, the icon is not displayed. However, note that as the aircraft descends below the activation altitude, the speckles within the cell boundary are displayed. 10,000 feet above the freezing level was the threshold chosen to activate the mid-altitude associated threat in order to give flight crews time to determine the best route of flight through electrified regions prior to reaching the vicinity of the freezing level. Remember that in the case of a mature cell-associated threat warning, turbulence and hail may extend well outside the cell boundary. Hail can be lofted out the top or sides of the cell, and shear effects may create significant turbulence as well. Therefore, MultiScan ThreatTrack extends the warning area outside the cell boundary to denote the increased threat of a mature cell. Note that the speckled region is not a threat boundary. In some cases, flight crews may penetrate this region without incident. Turbulence and hail might be present, but at a different altitude. Conversely, on occasion, turbulence and hail can extend outside the icon boundaries. The mature cell-associated threat icon is displayed at all altitudes during all phases of flight. There will be occasions where the associated threat icon appears suddenly. Notice this cell and the mature cell icon that appears as the aircraft approaches it. Remember that the total life cycle of a cell is about an hour. And for rapidly growing cells, the transition from the cumulus stage to the mature stage can happen in a matter of minutes. When the cell reaches the mature cell threshold, the icon is displayed. Mature cells often form an anvil top downwind of the thunderstorm. In these instances, hail can be ejected from the top of the cell and create a hail danger region downwind of the cell. At cruise altitude, MultiScan ThreatTrack's anvil top associated threat warning uses the upper level winds to define a potential region of ejected hail downwind of the cell. The region will be larger or smaller depending on the wind velocity. This is another reminder that, whenever possible, it is best to transit thunderstorms to the upwind side. The downwind threat region is activated when the aircraft climbs above 25,000 feet. Notice here that below 25,000 feet, the mature cell associated threat icon is centered on the cell. Climbing through 25,000 feet, the icon shifts direction to orient along the upper level wind axis and increases the downwind length in direct proportion to the wind velocity. It is important to understand that all associated threat warnings are inferred threats based on the nature of the thunderstorm that the radar has evaluated. In other words, the red speckles do not indicate a directly detected threat. The radar cannot actually see hail and turbulence in the red speckled regions. Thus, directly detected weather always takes priority over the red speckled associated threat icon. For instance, in this scenario, if it is necessary to transit this region, then the preferred route of flight takes the aircraft through the red speckled area. The flight crew would not turn left into the weather that is painting yellow to avoid the red speckled area in front of the aircraft, even though the yellow cells do not appear to be electrified. The red speckled associated threat icon is designed to give flight crews a more complete weather picture and enable them to make better avoidance decisions. Whenever possible, speckled areas should be avoided. Here's a second example of directly detected weather taking priority over the associated threat icon. In this scenario, if it is necessary to transit this region, pilots should maintain proper distance from the directly detected red cell core, even though the green region contains the inferred threat represented by the associated threat icon. Thus, for this situation, this path represents the safest and most fuel-efficient flight path. However, remember, speckled regions do represent significant hail and lightning potential. Therefore, whenever possible, these regions should be avoided. To illustrate, note that right as the aircraft arrives at the edge of this mature cell associated threat icon, the radar indicates fail and ground clutter flashes on and off the display. This occurred due to the fact that the aircraft was struck by lightning and once again emphasizes the need to avoid the speckled regions when practicable. In summary, remember these key aspects of the Rockwell-Collins MultiScan ThreatTrack radar. Core threat analysis more closely relates the color of the cell on the ND to the actual thunderstorm threat. Predictive overflight measures a cell's growth rate and then predicts the turbulence bow wave above the growing storm. When turbulence is predicted based on the rapidly growing cell beneath the aircraft, a predictive overflight icon is displayed. Because predictive overflight is based on a measured thunderstorm growth rate, pilots should avoid the region overlaid by the icon. Two-level enhanced turbulence paints severe turbulence as solid magenta and ride quality turbulence as speckled magenta. The red speckled associated threat icon is displayed in three different ways. Mid-altitude electrified cells have red speckles contained within the cell boundaries. For mature thunderstorms, the red speckles are extended outside the cell to show the potential for turbulence and hail outside the cell boundaries. And finally, above 25,000 feet, upper-level winds are used to predict the anvil top. So this icon will turn and align with the wind direction and extend downwind based on the wind velocity. It is important to remember that MultiScan ThreatTrack's associated threat is an inferred threat. Therefore, painted weather should always take priority for avoidance decision-making. The mid-altitude associated threat warning is displayed when the aircraft is less than 10,000 feet above the freezing level, and the anvil top associated threat region is extended downwind of the cell above 25,000 feet. The mature thunderstorm associated threat is displayed at all altitudes in all phases of flight. Note that when an aircraft commences its descent, the ThreatTrack software automatically scans down along the aircraft descent flight path, so it is no longer necessary to momentarily go to manual at top of descent, as in previous versions of the MultiScan software. Rockwell Collins recommends that the radar be operated in auto, cal gain, and weather plus turbulence plus hazard in all phases of flight in order to take advantage of the MultiScan ThreatTrack safety features. MultiScan incorporates more than 15 new and patented technologies to enable automatic radar operation. But the three major ones we will examine here are beam-to-beam power comparison, automatic temperature-based gain, and geographic weather correlation. In addition, the new ThreatTrack software described in Module 3 utilizes a track-while scan capability that will be described at the end of this section. But before we describe these technologies, let's talk about the technical obstacles that must be overcome to build an automatic radar. So here's a question. When a radar beam paints a target, does the return contain discrete digitized data that can be separated into different components, like terrain and weather? Or is it a single energy pulse that is composed of all the data painted by the radar at a particular range? The answer, of course, is that it is a single pulse that basically says there is something or some group of things at a particular range. And if you remember from Module 1, it is a pretty wide diameter pulse as well. When operating the radar manually, one method for distinguishing between ground clutter and weather is to raise the tilt to reduce the clutter. Unfortunately, this also tends to reduce the intensity of the weather return and limit the range that weather can be seen. In addition, with certain types of terrain, such as the cliff face displayed here, very strong returns can show up further out on the edge of the beam and unexpectedly introduce ground clutter into the picture, even with a high tilt setting. Cities are even a greater problem because man-made structures are very strong radar reflectors and again introduce clutter into the radar return. The original technological breakthrough for MultiScan was beam-to-beam power comparison that enabled the radar to eliminate ground clutter. MultiScan eliminates ground clutter by first using an internal terrain table to draw a line that is conformal to the Earth's surface. The radar then sweeps the area in front of the aircraft at a predefined tilt angle that is dependent on the height of the terrain. Returns are stored in a temporary memory buffer. A second sweep is then conducted at a slightly higher tilt angle. If we examine the exact same returns from the first and second sweep, we will discover that they have different strengths or power due to the different tilt angles. By doing a power-to-power comparison, it is possible to determine if a return falls below or above the conformal line. Returns that fall below the line are eliminated as ground clutter. Returns that are above the line are considered to be weather. This method of ground clutter removal also has the benefit of removing clutter caused by challenging terrain and cities. This picture shows the difficulty of distinguishing ground clutter from weather at longer ranges, even with the use of excellent manual operating techniques. In auto, MultiScan uses the beam-to-beam power comparison to eliminate the ground clutter, and the weather is now clearly visible. Once MultiScan has eliminated the ground clutter, all the weather in front of the aircraft is stored in the memory buffer. However, if all the weather was shown, it would result in many unnecessary deviations. So the radar uses the same beam-to-beam power comparison to measure cell height and determine the cells that reach the aircraft altitude. In this case, the radar draws a line that is approximately 6,000 feet beneath the aircraft. This is a curved line that conforms to the curvature of the Earth. In a similar manner to the way the radar removes ground clutter, an initial sweep records returns and stores them in a temporary memory buffer. The second sweep at a different tilt angle then enables a power-to-power comparison to see if the top of the cell falls above or below the line. The radar then chooses to show only weather that is at the aircraft altitude. This quiet, dark cockpit concept is designed to reduce crew distractions and prevent unnecessary deviations. If only the edge of the beam were used to determine cell height, the effective range would be limited to 40 to 60 nautical miles. With MultiScan's beam-to-beam power comparison, cell top measurements begin at 120 nautical miles, with a goal of an accurate display of threat weather that is at the aircraft altitude by 80 nautical miles. These pictures show the end result. Note the weather at 30 and 70 nautical miles, and also note the weather coming onto the display at 180 nautical miles. And finally note that the low-level weather is not displayed. In actuality, accurately determining the tops of cells is more difficult than just measuring cell height due to the fact that the tops of most cells are non-reflective and also because of the variable nature of weather around the world. So let's examine some of the weather science that must be considered for accurate cell top measurement. First, let's look at the composition of a typical thunderstorm. Thunderstorms can be described in two ways: what you can see with your eyes, what is visible, and what the radar can see, what is reflective. The tops of thunderstorms are composed primarily of ice crystals and are poor reflectors of radar energy. Thus, thunderstorms have both a radar top and a visual top, and the two are seldom the same. In the case of growing storms, the extent of the thunderstorm threat extends well above what the radar can actually see, and includes both the cell top and the turbulence bubble that is pushed above the growing cell. Automatic temperature-based gain is the first technology that is used to deal with non-reflective cell tops. You'll remember from Module 1 that automatic temperature-based gain increases gain as the outside air temperature decreases. Thus, at cruise altitude, manual max gain and auto cal gain display similar results. Essentially, this reduces the non-reflective portion of the cell so that more of the actual cell top is visible to the radar. Remember from Module 2, what does green mean? That this results in more energy on target at cruise altitude than most pilots are used to seeing. Please review Module 2 for proper radar interpretation in light of this increased gain. Let's also look at how weather varies based on geography to understand the third technology, geographic weather correlation. Scientists have long known that thunderstorms display very different characteristics depending on where they are in the world and whether they develop over land or over water. For instance, a typical Central African cell has very strong updrafts that carries water content to high altitudes. These cells also exhibit significant convective activity well above the freezing level. A Central Pacific cell, on the other hand, might look very similar on the outside, but its internal characteristics are vastly different. Updrafts are not nearly as severe, and thus high-altitude moisture content is far less. And most convective activity is much closer to the freezing level. This chart is one of many by Dr. Ed Zipser, one of the world's leading climatologists, that depicts the worldwide variation in thunderstorm development. Note that continental land-based cells have strong reflectivity characteristics at cruise altitudes, while oceanic cells have very poor reflectivity characteristics. Equatorial land-based cells fall somewhere in between. Note these weather pictures and how closely they correlate with the chart. The right-hand cell has significant convective activity and provides excellent reflectivity characteristics. In contrast, the oceanic cell on the left has much less mass and much lower reflectivity. The green, yellow, and red colors at the bottom right-hand corner of the chart equate to the standard radar reflectivity levels. Note that if the radar is set up for proper weather detection of this continental land-based cell, it will show up on the display as yellow or red. However, if radar settings are not adjusted to account for the different cell characteristics over the ocean, then the cell will not even show up on the ND. The problem is made even more difficult due to the fact that these regional variations in weather change depending on the time of year and the position of the ITCZ, or Intertropical Convergence Zone. In recent years, scientists have used new weather satellite systems to analyze and catalog tens of millions of data points that have enabled us to develop robust geographic weather models for weather around the world. MultiScan incorporates these weather models into a worldwide database that resides inside the radar. Using a 10-degree by 10-degree geographic grid, the radar sets thresholds based on geographic position, time of year, and whether the aircraft is over land or water. In regions where thunderstorms exhibit very poor reflectivity characteristics, thresholds are set low so that when the radar detects moisture at lower altitudes, it can predict that the cell top reaches to the aircraft altitude. In regions where thunderstorms display strong reflectivity characteristics, thresholds are set higher to prevent the radar from overwarning and causing unnecessary deviations. Thus, thresholds are matched to weather characteristics in a particular geographic region to determine the actual cell height and to best display the actual thunderstorm threat. Finally, MultiScan's new ThreatTrack features that are described in Module 3 are enabled with a track-while scan technology that tracks up to 48 thunderstorm cells while scanning the area in front of the aircraft for additional threats. The radar determines each cell's relative threat and then schedules individual cells for detailed analysis in order of threat priority. The vertical sweep used by the radar essentially produces a nowcast of the storm's relative severity. Essential elements that are used in the threat evaluation include severity and height of the convective activity in the cell, temperature, cell growth rate, and upper-level winds. This analysis then enables the directly measured and inferred MultiScan ThreatTrack features described in Module 3. In summary, MultiScan ThreatTrack radar contains a decade's worth of technologies that drive the radar. But the four fundamental elements are beam-to-beam power comparison that enables ground clutter removal and cell top measurement, automatic temperature base gain that allows the radar to better see non-reflective cell tops, geographic weather correlation that enables the radar to better predict actual cell tops in the different regions of the world, and track-while scan technology that enables detailed thunderstorm analysis and activates the ThreatTrack warnings.